So good morning. Perhaps I can close this. Morning. This is the second lecture on quantum thermodynamics and relativistic hydrodynamics. That's the title of my set of lectures. And so let me summarize what we have seen yesterday very briefly. So what we have seen yesterday is the introduction of a quantum framework to approach the dynamical process of quark-gluon plasma evolution and relativistic heavy-ion collisions, which is based on this diagram. So we have a space-time region where we have QGP. And as I mentioned yesterday, what we need to know in order to solve any problem in quantum mechanics and quantum field theory as well is the density operator. So the density operator should describe the initial conditions, which means, in principle, the two nuclei colliding. Okay, so it would be something like, the product of two cats, two nuclei with different momenta incoming. But solving this problem is extremely difficult. Okay, and therefore, what we do is that we choose to approximate the true density operator, which at a later time in the Schrödinger picture would be given by this. Say later time T naught, okay, would be given by this operator here, okay? This is in a non-covariant picture where you have a hypersurface at fixed time where this is calculated. We choose to approximate this density operator at a later time. In fact, this density operator should be rather written like this in a covariant form. Where this is the hypersurface, this is a space like hypersurface that we choose, okay, that we assume that we know something, okay, some hypersurface. This is a Killing vector, okay. This is something that need to be specified in order to, tell what the time is, okay. We can choose this simply as 1, 0, okay. And this hypersurface in relativistic heavy-ion collisions is most commonly chosen. This was the something discussed at the end of the lecture yesterday. Is chosen something like a hyperbola or something looking like an hyperbola, okay, at some time. Crossing the time axis at some time tau naught. And over this hyperbola, this density operator is assumed to be given by the local thermodynamic equilibrium density operator. So in other words, we assume that we can replace this one, which would be the true one, with rho local equilibrium. And I will tell you in this over this lecture what rho local equilibrium is or what it looks like. Okay, so what we want to know is how does it look like? So how can I write down a local equilibrium density operator. And to learn this, I have started with a simple problem. The simple problem is what a global equilibrium density operator looks like. So from this, it will be then natural to obtain this, okay? So from the global to the local. So the global equilibrium density operator has been obtained yesterday by maximizing the entropy written in a proper quantum framework with constraints or assigned or fixed mean values of the conserved global quantities, the energy, the angular momentum, the boost, and the charges. And this has been written as a function of 10 constant. Plus charges, where B, omega, zeta I are constants. In fact, this is a vector. This is an antisymmetric tensor. So we can write this like, oh, sorry, this, yeah. We can use the indices or the compact notation with a column in order to, which stands for the double contraction. So these objects are constants. They are the Lagrange multiplier of the maximization problem of the entropy with constraints. And now, and this is the most general form in special relativity, okay? So that is the most general form of a global equilibrium, which includes all the, say, special cases that one may think of. For instance, the usual global homogeneous thermodynamic equilibrium, which is associated to the density operator e to the minus Hamiltonian over temperature that everybody should be familiar with, as well as more interesting cases, or more exotic, if you wish. For instance, we have seen yesterday the rotational equilibrium, which is a system which is rigidly rotates around its axis, which is described by the e to the minus Hamiltonian over temperature plus omega over temperature Jz, where this is the generator of the angular momentum. Okay, this is the angular momentum operator indeed. Okay. Now let me write this P mu more in general. Let us write this P mu and J mu nu in a quantum field theory. They are given by integrals of stress energy tensor and associated quantities. In fact, we have seen yesterday that P mu here is equal to d sigma lambda T lambda mu, okay, over some arbitrary hypersurface, provided that you have, say, an outward, you have a, say, vanishing boundary fluxes, okay? So you can write this as an integral, and you do not need to specify which hypersurface you're integrated on, okay? Because it might be any space-like hypersurface. Similarly, for the angular momentum boost generators, there is a formula from which tells you that this is equal to this x nu t lambda mu, okay? Again, you don't need to integrate to specify which hypersurface you're integrated on, because that can be any space-like hypersurface. The point is that the divergence of the integrands, of both integrands here, is zero. And similarly, for the charges, there is always a conserved current, vector current, J lambda. And again, you can write this Qi as an integral over some arbitrary hypersurface of a current vector operator. Okay, so now the task is to plug this expression in here. So what we get is the following. Rho global equilibrium is equal to 1 over Z. And we have an exponent of minus d sigma mu. Okay, let me write T mu nu. And we have here B nu plus omega nu lambda x lambda plus let me see. Okay, that is minus minus, sorry. And then we have zeta, some I, zeta I, j mu. Okay? So what I have done here, I have simply taken this omega mu nu and multiplied by j mu nu. Okay, I put it into the integral. I took advantage of the antisymmetry. So in fact, I have 1/2, but I have two terms, which because of the antisymmetry of omega mu nu, they result in twice, okay, in 2 times the same term. Therefore, I can write down in a compact way this global equilibrium like this, okay? Well, I mean, I have skipped some step, but you can do it step by step if you wish to check it out, okay? Now, can be written as 1 over Z. Okay, this is important. This is called the partition function, okay? And it is simply a normalizing factor to make this trace, the trace of rho equal 1, as it should be. So don't forget about this very important constraint that every well-defined density operator should have trace equal 1, right? Because of the unitarity of probability. So the sum of all probabilities should be 1. Okay. Now, so whenever you see something like this, 1 over Z, this means that Z is the trace of this exponent. Okay. In order to make the trace equal 1. Okay. Now 1 over Z, and then we can write minus d sigma T mu nu beta nu, where beta is this vector here, minus, and then we have, well, I mean, for the sake of simplicity, let me just write down one single charge, okay? So I have emphasized enough, I think, that you may have different currents here. Also an index I should be here. But let me now confine myself to just one conserved charge. This is for the sake of simplicity. Okay, then minus zeta j mu. Okay, so now I have written this global equilibrium in a very interesting form because I have now a single vector field beta, okay, which is usually called exponential, yeah. So so now I have that beta nu is usually called for temperature or inverse for temperature vector. We will see from the, for the present, we are not able to give this 4 vector a physical meaning. Not yet, but it will become clear in my 3rd lecture that we can give this vector a physical meaning. So let me just tell you in advance what this physical meaning will be. And the physical meaning of this 4 temperature, you may guess from this naming, is that beta squared, which means beta nu, is equal to 1 over T squared, where T is the temperature which is measured locally. That means via co-moving thermometer. Plus the versor associated to, so the unit vector associated to B can be taken as a definition for velocity in the hydrodynamic frame, in the hydrodynamic model. And this also defines, this is associated to the so-called thermodynamic or beta or thermometer frame. It's a particular frame among all frames in relativistic hydrodynamics that you may choose, okay? Because it's a for velocity. So in order to understand, in order to establish the physical meaning of this, of beta, you need to wait, yeah, okay? You need to wait the 3rd lecture, so you need to wait tomorrow morning, okay? Well, it become clear by comparing with classical thermodynamics or relativistic classical thermodynamics that this definition, that this physical meaning is there, okay? The individual, oh yeah, that is simply u mu, beta mu. So once you know that, you know what is the physical meaning of the magnitude, beta squared, and then all the individual components, have obtained this but just by dividing beta mu by square root of beta squared. Okay, so you have 4 degrees of freedom. So you have a 1 amplitude, which is the temperature, or 1 over the temperature, and then you have 3 components for velocity, because u mu, of course, is equal 1. Okay. But let me put this aside, as I said, for a moment, and let's continue with this. So if I have this form, well, another interesting point is the following, is that this form of beta nu, okay, as you see that it includes a constant 4 vector and a constant antisymmetric tensor, okay? You can write omega this way. Of course, this is a trivial equation because from this expression, knowing that omega is a constant, okay, you can take, say, beta nu, plug it in here, and then you realize that this equation applies. However, later on, when we will talk about a local equilibrium, this will become an equation defining what is usually called thermal vorticity. So you have seen a vorticity today. This is not the same vorticity I'm talking about. This is a vorticity which involves the antisymmetric derivative of the 4 temperature. And this is usually called thermal vorticity, just because it includes derivatives of the temperature in a sense, because it is a derivative not of velocity field, but a 4 temperature field, okay? This plays a very important role in for instance, in the spin polarization business, and but also in geometry of the, so in the say in general relativity. When we try to extend this global equilibrium to general relativity, you will see that this is also very important. Okay. Yes, a question. Yes, please. Oh yeah, you can derive from this. I mean, once you know that beta nu is equal to B nu plus omega nu lambda x lambda, you just take the derivative with respect to lambda. Okay, this is 0 because this is a constant, and you get omega nu lambda. Okay, then you change, and then you get this. You know, Okay, but I mean, it looks like, you know, it does not look necessary for the present. This is just to tell you something in advance, that this for the present is just trivial, because that is you know, the form of beta nu, and therefore of course the omega follows. Okay. However, but in general, then this is assumed then in the more general form when beta is no longer given by this expression. Become clear that this is maybe later on in this lecture, this may be taken as a definition indeed. Okay. Now, this form of the global equilibrium is very suggestive. Okay, it's very suggestive because it has a form. First of all, it has a form which looks like being extendable very, I would say, straightforwardly to a general relativity, because it involves integration of a 3D hypersurface, which is quite a general concept, regardless of the fact that the space-time is flat, and stress energy tensor and beta nu, and the vector field, and the scalar with a vector field. So it looks like really a very, I would say, general relativistic expression, because in this form here, and those of you who are familiar with general relativity know that in general relativity, x lambda here cannot be a vector. So it's not a vector field. It is a vector field only in special relativity, and only if the coordinates are Cartesian. Otherwise, this is not a vector. This kind of expression is therefore only suitable for flat spacetime, and if you describe spacetime with Cartesian coordinates. For instance, if you describe this with Rindler coordinates, or which are more suitable for, say, the Bjorken flow, that this would not be applicable. Okay. Therefore, whereas in this form here, that in a sense, well, this case can be more general, because that I have a general vector field beta, I have a scalar, so that is perfectly general relativistic. Can be written in this form, that this is applicable to any coordinate system. Okay, I can choose, you know, spherical, or I mean, I can write down the covariant components of a vector field. So this leads us to also to the concept of local equilibrium quite naturally. And how to do this? Well, assume that you have a hypersurface, okay, where you know what are the values of the energy and momentum densities. So assume that over this hypersurface, what you know is the energy density. So you know the momentum density. And you want to maximize entropy by forcing the energy density, the momentum density to be at any point, at all points of this hypersurface, to be some assigned value. Okay? This corresponds to implementing the concept of local thermodynamic equilibrium in a quantum statistical framework, because when you think about local equilibrium, what you imagine, what you can imagine in your mind is that you have a situation where at different points, like for instance in this room, we know that we have a different temperature here compared to there, okay, or to here where I'm standing. So we have different energy densities of the air at different points. Okay, and if you want to write down what is the operator representing your say maximal disorder or minimum say knowledge, okay, minimal knowledge. Once you know what are the energy density, the momentum density everywhere, then what you would do is that you would maximize the entropy with constraints of given mean values of energy density and momentum density everywhere in the room. That corresponds to, in a sense, to localize a thermodynamic problem in all points in the space, okay? So in other words, you would write down this entropy, okay, adding some constraints whose say purpose is to say forcing the energy density and the momentum density to be those who are somehow known, okay? Just like so in a sense, this corresponds completely to the problem of global constraints for the global equilibrium. Now, what is the energy density and momentum density if you have a general hypersurface 3D like this? Well, they can be written as a function of the stress energy tensor like this: T mu n mu T mu nu, where n is simply the vector which is perpendicular to the hypersurface. Okay, this is indeed a field because it depends on the point, so it is different at different points. In space-time, you know, the orthogonality is not really orthogonality in Euclidean sense, but one should make, you know, one should draw the light cone and make this reflection with respect to the bisector. Anyway, doesn't matter. Important point is to understand that this is an orbital vector to the hypersurface. So the energy density and momentum density can be written in a covariant form with a compact form like this. Okay. So if you know the stress energy tensor, the energy density and momentum density can be written as a projection of T mu nu onto n mu. In fact, if you take a special case, n mu equal 1, 0, for instance, hyperplane. In this case, this is easy. This is 1, 0. Then this would correspond to T0 nu, which is precisely what one would say expect to be the energy density, 0 component, and the momentum density, the space components. So in a covariant form, this is n mu T mu nu. So let's stick to a covariant formalism. And then I have to maximize the entropy. And then I have to introduce some constraints, okay? And I have to constrain the energy density, momentum density over the whole the hypersurface. And so what you have to do is that you have to have an infinite number of constraints, okay, for each space-time point. And this is an infinite and continuous number of constraints. And so eventually what you do is that you have to write down an integral of constraints like this. So we have d sigma n mu T mu nu. Okay, I have to write Okay, let's be precise. So trace rho T mu nu minus T mu nu assigned or true, if you wish, beta nu x. So let me, what I have written down here is the function to be, so this is not S, this is a function of rho to be, and I have to find the extremal of it, okay? So much the same way as we have seen yesterday for the global equilibrium problem, where I have an infinite number of constraints, okay? So this term with this factor within the brackets means that I want the mean value of the stress energy density tensor to be the assigned value, okay, to be some true energy and momentum density. And this function plays the role of Lagrange multipliers, okay? So this is a function which means that this is a Lagrange multiplier point x1, point 2, point 3, and so on and so forth. Please. Oh yeah, that is and mu, right? Yeah, because this is, I mean, I did not, well, I mean, I'm assuming, or if you are not familiar with some differential geometry, say, basics, that is, when you integrate over hypersurface, then you can split this into the product of d sigma, which is a measure, and this is equal to d3 coordinates, d3u times, then there is a determinant of the metric tensor reduced. No? I don't know if you are familiar with this approach. This is just a generalization. This is an extension of what integration means over some not flat hypersurface or hyperplane, in other words, okay? Now, so we have an infinite number of constraints. This problem can be solved. Okay, I should add plus something for charges. Okay, should not forget that. And eventually, what I get is that the solution of this problem exists. And then I can write down the local equilibrium density operator like this. Okay. So this is the result of this maximization problem. Yes, please. Sorry? The minimum, oh yeah. You mean that there is an error here? Okay. Yeah, perhaps, yeah. Most likely there is, yes. So I should have written minus. Yeah, thank you for pointing this out. By the way, yesterday I also, yes, you are completely right. And then I must have, okay. Yeah, thank you for pointing this out. Yeah, there must be a minus here in order to find the maximum of entry with constraints. And then the solution is written here, okay? And that is very important because now we can compare this with the global equilibrium, and what we find is that now beta, which is a Lagrange multiplier, general Lagrange multiplier, so a function of x which should be calculated, becomes something particular, this at global equilibrium. So this is clearly an extension of the global equilibrium to local equilibrium, which has precisely the same form, okay? So beta nu x is a function which can be determined by solving this equation, solving the equation of constraints. So if we calculate now if you were able to calculate this, okay, now that we have found this rho local equilibrium, and we know that it has an exponential form, we can, in principle, obtain this, solve this, calculate the expectation value of T mu nu, okay? And if we were able to calculate this, and this is depends, of course, on beta. Okay, let me write this from now on like this. This is something which depends on beta, and I put it within square brackets because it may depend on beta in a very complicated way, because in fact, it appears here in the exponential of an operator. Therefore, what we expect is the dependence of T mu nu of x. Dependence is of functional type, so it depends on the whole function, not just on the beta at the point x. This is an important point to be stressed. But so we should not forget, I mean, that we have a constraint, as I said, that we have enforced that n mu T mu nu local equilibrium, which is the mean value with this operator newly found, should be equal to the assigned or true value of the stress energy tensor. That means that beta will be a solution of this equation. So beta can be found by solving this equation, and it has 4 indices, okay? Because you have energy density, momentum density, so I have 4 independent components, and I have to find out a function, which is a 4 vector. That's a problem which, in principle, can be solved, okay? So beta nu is obtained by solving this constraint. And what is special about beta nu at global equilibrium? Well, I can rho local equilibrium. It is something that it is not independent on sigma. Actually, it has been obtained by integrating over some specific hypersurface. So I have been given a specific hypersurface where the energy momentum density are known, and then I have found what is rho local equilibrium, and it is written like this. But now it depends on the hypersurface. And then I may wonder when this local operator becomes independent of hypersurface, which is a statement in relativity equivalent to the good old one in classical mechanics, when is rho independent of time. Okay, every time I have something which is independent of hypersurface, this translates immediately in our classical attitude or reasoning that this is independent of time. So when is this independent of time, which should be formulated more precisely? When is this independent of the hypersurface? Well, some integral is independent of the hypersurface provided that you have an integrand which is zero divergence. So you have divergenceless integrand, and you have some vanishing boundaries, vanishing fluxes at the boundary. In other words, I can try, okay, if I want to answer this question, is that I can try to see or to investigate when nabla mu T mu nu minus Z zeta mu is equal to 0. In this case, I would expect that this rho local equilibrium becomes independent of time, independence of the hypersurface, and most likely it will coincide with rho global equilibrium. So let's see if this is the case. Nabla mu T mu beta nu minus Z zeta mu integrand equals 0. But I know that nabla mu T mu is equal 0. These are conserved. Also, I know that nabla mu J mu is a conserved current. Okay, so what I'm left with is this equation. Okay. So when is this realized? This is realized when, this is accomplished when T mu is symmetric. So I just need this to be antisymmetric. So if this is 0, then of course this term is 0. And besides, if nabla mu zeta is 0, also this term is 0. So I have two conditions on the Lagrange multipliers, on beta mu and zeta. This equation that I have purposely written with a nabla instead of partial derivative, because I want to emphasize that this conclusion applies to general relativity as well. So everything that is written here is really generally covariant, okay? So I can use covariant derivatives instead of partial derivatives in order to make it even more general. So this equation here is a very well-known one in differential geometry. And it is equivalent to something that maybe some of you know, that the lead derivative of the lead derivative, this is equivalent to say that the lead derivative along this field beta of the metric tensor is equal to 0. This is called Killing equation. Sorry? This is the Killing equation. So this is completely equivalent to this. So these are two forms. Sorry. The second term. Oh, right, sorry. Yeah. Yeah. Thank you for pointing this out. Yeah, of course. That is because this is symmetric. Therefore, in order for this to be 0, you just require this. This is called Killing equation. And it is the equation defining what is a symmetry in general relativity. This is a very important point. In special relativity, we know the full solution of this equation. This is a partial differential equations which depends on 10 constants, and we know that the solution, the general solution in flat spacetime is just beta equal constant plus an antisymmetric tensor x nu. Okay, so this is the most general solution, and we are back to this global equilibrium as I have told you. Okay, so in other words, enforcing this to be independent of time, we go back to the global equilibrium. Okay, so this reinforces our confidence that this is the correct form of the local equilibrium, of the density operator representing local thermodynamic equilibrium. Okay, good. There is one more, yeah. Because let me just conclude by saying that this nabla mu zeta equals 0. This is obvious. Okay, this becomes just zeta as a constant. Okay, and this is quite straightforward or trivial. How did we end up with this? That is a good question. That is, T mu nu is symmetric. No, it should be plus. Because you can write down T mu nu should be plus, because then you can write down this. So the same this product, if T mu is symmetric, you can write down like this. This is completely equivalent. In other words, or if you wish, you can decompose this into a symmetric and an antisymmetric part. The antisymmetric part would contract with this and yield 0, and therefore you're left with this. Therefore, if this is to be 0, then so this is in other words, the sufficient condition for this having 0 here, and this contraction is that nabla mu beta nu will be an antisymmetric tensor, so that its symmetric part should vanish. Okay. Which function? This one. No, I mean this is a sufficient condition. So you want this to be 0, okay? You want this to be 0 in order to make this integrand vanishing, right? Okay. There was a question. Yeah, please. You have to speak louder, sorry, because I. Yeah, this is another good point. So I have assumed that this is symmetric. You may relax this assumption, but then it becomes more complicated. So the local equilibrium here operator becomes more complicated. So you may extend this approach to the case where you have a non-symmetric energy tensor, and at the same time you have a spin tensor. Okay, but the conclusion would be unchanged. Let me say this. So you will get to this again, but then we can, if you are interested in, I can show you how to do this with a general spin tensor. What happens is that if you have a non-symmetric tensor, you will have an additional term in here involving the thermal vorticity, so omega mu nu, and the spin tensor, okay, which I have not talking about so far, but it can be. But this conclusion will hold, okay? That beta should be a Killing vector anyway, in order for have an independence of time or independence of hypersurface. Yeah.
So you said earlier that Google reason that one trying to pay you because
No. I did not know. That is beta mu for our global equilibrium. Beta mu, global equilibrium in flat space-time. That is important to emphasize. Beta mu is given by this equation. Okay, that we have seen at the beginning of the lecture. So that we have beta. So it depends on a constant vector and a constant antisymmetric tensor. But this is a fully covariant expression. This applies to any frame. So I did not go to any special frame in order to get this. Okay. And then what we have found is that this is something which can be derived by requiring that beta is a Killing vector. Because this is just the general solution of this equation. Okay, so this is a partial differential equation. It looks like very, very general, but it is very constrained. Okay, so in flat space-time, it has a very, it has a specific solution, which is given by this, Yeah, that is true. In the global equilibrium, I know what he's probably talking about when you have an external electromagnetic field. Yes, I think this approach can be extended to if you have an external field. In this case, that nabla mu T mu nu. In this case, you have an external field. Nabla mu T mu nu is not equal to 0. Okay, but for instance, if you have you have the Lorentz force. And now in this case, you have that the nabla mu zeta is no longer 0, but you have something which is the electric field. But if you have an isolated system, so without external field, then the zeta, which is the ratio between mu and t, should be constant. That is absolutely, say, I would say, specific, yeah. This is well known. Okay, so I think that we can, well, I'm a little late on the schedule, so we can stop here, I guess, and resume in 10 minutes. Finally, attacking the problem of dynamical problem of relativistic heavy ion collisions in a quantum statistical framework. Okay, also what I have said is that so we have a hypersurface, which is most, say, at high energy is chosen to be a hyperbola, but it can be anything, principle. Okay, which is from now on will be denoted as sigma naught. We have a hyperbola where the state of the system, to a very good approximation, or hopefully good approximation, that we don't know. I mean, this depends on the final results, of course, of analyzing the data, is the local equilibrium operator. Okay. Okay. So we know. So we take as a good approximation of the state of the system at some time, or which means at some hypersurface, we take this expression. Okay? And that's it. Now, our goal is to calculate the mean value of anything. I would say of any quantum operator at the point x later, I mean, means later in the sense in the future of this hypersurface. Our task then is to calculate with this, let me call this instead of local equilibrium, well, I mean, I can denote this as, okay, 0, yeah, for a reason that will be clear in the following. So that's it. I mean, our problem is now fully, say, expounded. But then we can now try to calculate the mean value of any operator. And when I say the mean value of any operator, we can also include the mean value or the fluctuations of an operator. So I can calculate a 2-point function or a quadratic operator or anything at some point x here, because now we know what is in the Heisenberg picture, okay? That means that this depends on space and time as well, at some, with a given density operator. So now the goal is try to calculate this, will be denoted by OX simply. Okay, so this is the mean value, or the best approximation to the mean value that we may think of. At some later time, because now we know what is the the state of the system. We know this, okay? And so in principle, it is a well-posed problem. And we can apply this to, for instance, if we want to solve the hydrodynamic problem, okay? We can replace with T mu nu instead of O. So we may want to calculate what is the mean value of the stress energy tensor at some point x here or here or here, anywhere. This is a more general, say, view than relativistic hydrodynamics. So this is a, say, this is a quantum problem. So it means I want to calculate something at some future time once I know the state, okay? Of course, it is easier said than done, because calculating this mean value is absolutely a formidable task, because it involves the dynamical evolution from this hypersurface to this. And this, in turn, goes back to the solving the problem of QCD. So this problem can be solved in principle only if I knew how to solve the partial differential equations of the operator of QCD, or I can try again to obtain a good approximation by using some suitable method, suitable for what? For the system that we are dealing with. So a quark-gluon plasma, so we believe to be dealing with. So a quark-gluon plasma, which we believe it stays close to local equilibrium for at least a large fraction of its lifetime. And this is what the data, I mean, the studies that have been done over the last 20 years confirm. So there is now, I would say, a reasonable belief that the quark-gluon plasma lives at least a very high energy for a long time in a state which is close to local thermodynamic equilibrium. So I'm going to say now, what I'm going to explain in this quantum framework, what close to local thermodynamic equilibrium means. Because for the present, we have been using this local, this local thermodynamic equilibrium only at some initial hypersurface. Okay. Now we want to know what this notion of being local, close to local thermodynamic equilibrium in the future means. And to do this, we will be using the Gauss theorem. Okay, again. And now I can use this. Let me use this. The slides that I have, one slide that I have prepared. What is it? Okay, here it is. Okay, what does Gauss theorem means? Well, what is the? Suppose that you have some past time hypersurface, okay, which can be identified with this one, okay, the relativistic area collisions. And suppose you want to know what is the mean value of something at a later point x. Now, what you can do, if you have a good reason to believe that over this space-time region, the system stays close to local thermodynamic equilibrium, whatever it means, you choose a hypersurface which crosses or say the point x belong to, okay, with its normal perpendicular vector, some arbitrary, I would say, hypersurface crossing the point x, and then you close the region omega, this one, by choosing two boundary hypersurfaces, which possibly can be extended to, say, to the infinite distance on the right and on the left. And you write down your Gauss theorem, which says that if I integrate over the whole, say, boundary here, so this is a boundary made of 3D hypersurfaces, just to, so was a question in the, just to be accurate, when I talk about 3D hypersurface, so when I talk about the hypersurface, I mean a 3D submanifold, okay? So all of them are 3D hypersurfaces encompassing a 4D region in space-time. I can write down the Gauss theorem. And if I confine myself to just the part of this operator involved in the stress energy tensor, so let me forget about this current for the present. So it does not change the final result, the same. Then what I can write down is that minus, because I have inverted here the sign of n, should be, in the Gauss theorem, this should be directed backward, minus d sigma mu t mu nu beta nu plus d sigma mu t mu nu beta nu at the hypersurface sigma is equal to the integral of nabla mu t mu nu beta nu. We have seen already this in when I derived global equilibrium from local equilibrium. Okay. Now, the only difference being here that this term is not expected to be zero because beta is not necessarily the solution of a Killing equation. So this is not necessarily global equilibrium. Beta can be an arbitrary, or can be, is a four-vector field which is obtained by enforcing that the energy momentum density is known at the hypersurface, but otherwise that is does not need to solve the Killing equation. Therefore, this integrand is not zero. So the divergence of this vector field is not zero. Nabla mu t mu nu is zero. Therefore, I will left with t mu nu nabla mu beta nu. If the boundaries are chosen in a way that, in such a way that this boundary fluxes vanishes, so that I have no contribution from this blue hypersurfaces, then what I'm left with is a very interesting equation, which tells me that minus the integral d sigma t mu nu beta nu, so this one is equal to the integral of sigma plus the integral of d omega t mu nu nabla mu beta nu. Okay, which is obtained by simply expanding this divergence of these two factors, because nabla mu t mu nu is zero, and then we are left with t mu nu nabla mu beta nu. So you say you can see that if this t mu nu nabla mu beta nu is zero, which means if nabla mu beta nu is antisymmetric, which in other words means if beta is a Killing vector, then you have this integral vanishes. But otherwise it does not. So in general, for an arbitrary, say, local equilibrium operator, this is not the case. And therefore, you are left with a rewriting of the density operator in terms of two terms. Then there should be also some terms from Karetz. Maybe I can write them down. Okay, this is a full form, including the currents. Now, why is this useful? I'm going to tell you. Okay, first of all, so let me say that means that if I have a point X, so let me now go to the case of relativistic heavy-ion collisions. I can choose hypersurface like this, okay? And maybe I can extend this to the point where this boundary do not contribute. So I can rewrite my state in this form, okay, where sigma t is this hypersurface here at a later time. So this can be chosen at some point that we are interested in, okay? So for instance, if I want to calculate t mu nu within the plasma, I want to choose a hypersurface which crosses this point within the plasma. In many circumstances, in heavy ion collisions, what we do is that we are interested in calculating something, guess when? Well, no. So, yeah, of course, we are also interested in this, but what is the most, I would say, one of the goals of say, the phenomenologists? Exactly. So we want to calculate something at the freeze out, so where the QGP falls apart and breaks up into hadrons. It is valid. It is still valid because this is valid anywhere. In other words, once you know that state, you can go up to infinity, and this still applies. Of course, provided that you are, say, careful enough to choose that a boundary which say, fulfills this condition. No, I'm not saying that the local equilibrium continues. But I will be more specific in that. I'm saying that this kind of equation applies to up to infinity. It is mostly useful when you are close to local equilibrium, because in this case, it means that you can approximate your calculation by treating this term as a correction. That is the most important point. Okay, you will see this. But in principle, okay, Gauss theorem, it's Gauss theorem, so you can apply it to the infinite future. It doesn't matter. It is mostly useful, of course, in some case, and then it's in some specific case. One of the hypersurface which is mostly useful, I'll say, that is the freeze-out hypersurface, which has, say, such a form. This is a drawing which may not be, say, accurate, but it's more like, more or less it looks like this. This hypersurface, which is called freeze-out hypersurface, is the hypersurface where we believe that the local thermodynamic equilibrium, the system is still close enough to local thermodynamic equilibrium to be, calculated in this way. Yeah? This has a special feature. So there is this is very interesting also because geometrically, because it has no boundary sigma L. So this hypersurface has a time-like part here, which connects directly to the sigma, to the hypersurface of the hyperbole initial state. That is why it is interesting. It also geometrically has a nice feature. So this, in other words, this condition is automatically fulfilled. There's no need to make any further request. And so now, let me come to the question of your fellow. That is, why is it that interesting? Why is this decomposition? It is interesting because it's application of Gauss theorem, but why is it useful? It is useful whenever you can identify in these, say, two terms, one which is prevailing or predominant, and one which is a correction. And when does it happen? It happens when you have a system which, say, you believe physically that it maintains a condition of local thermodynamic equilibrium up to some time, like the plasma, for along its evolution until, say, freeze out or particularization. In this case, if you have such a condition, this means that this is predominant. This is a large, or if you wish, this is a large term. And this is the small term. Okay? And whenever you have an exponential which has a large term and a small term, you can apply a well-known, say, theoretical technique, which is called linear response theory. Or linear response would be, say more properly, it is an expansion of the exponential in terms of treating this as a small correction. And so you can make an expansion. I will show you how to do that where you can stop, you can generally stop at the linear term, but you can continue, you can stop at quadratic or cubic or quartic and so on, okay? Now, when is this term small? So how to, it's not easy to see it because you are dealing with operators, so it's quite complicated. But you can look at this, at what is a function here. So you can look at beta, or nabla meter, and nabla mu beta nu, and nabla mu zeta. Well, it is presumably small when the gradients are small. So it means that when you have a situation where the gradients are, are there, of course, otherwise would be global equilibrium, but they are small. So they do not really, they are, in a sense, or if you wish, that the beta field varies very slowly. So it means, because you have a gradient small, means that beta varies very slowly compared to what? Well, in general, that so it can be realized just by working out this expansion that in general this happens if the scale over which these gradients vary is much larger. So assume that if, for instance, you fixed 10%, so you see, however, what is the distance over which that beta varies by 10%, for instance? This gives you some benchmark for how large the gradient is. Well, if this distance is much, much larger than the microscopically involved scales, which are the scales which are involved in our dynamical problem and can be related to a cross-section, sorry, it would be a mean-free path, okay, which is a distance, or say Compton wavelength, for instance. Okay? So if this distance is much, much larger than the microscopically involved scales, and microscopically are those relevant to the theory that we are dealing with, which is QCD. Therefore, a mean-free path of quarks and gluons, or say Compton wavelength of these particles. So Compton wavelength, if they are massless particles, is 1/T, so the thermal wavelength. So if this scale is much larger than that, then we are in a situation where this can be dealt with really as a small correction, and we can apply the expansion that I'm going to talk about, the so-called, which then corresponds at the lowest order to the so-called linear response theory. Okay? So, in other words, nabla mu beta nu divided by beta nu to be, so this has a dimension of 1/length, or if you wish, maybe it's even beta over nabla beta. Let me, use some loose formulation, which is this can be taken as the characteristic. This is a distance, the distance of significant variation of beta must be much larger than microscopic length. Yes, absolutely. Yes, yes. Well, no, I mean, sorry. Well, if Knudsen is the ratio, it has to do with the size of the system as a whole. Okay, so that is not, yeah. No, that is this is the requirement that the hydrodynamic scale should be much. This is also a hydrodynamic limit. The hydrodynamic scale, so how slow is the variation of these fields compared to the microscopic interaction length. Okay, microscopic lengths, like, well, if you are in a kinetic picture, this can be lambda, the mean-free path, or a Compton wavelength, or yes, exactly, yeah, which is also encoded in the mean-free path. Yes. Yeah, so this is called hydrodynamic limit. This is what is found once you expand this and you try to calculate the correction. So that you see, that of course, the hydrodynamic limit means precisely, it means exactly what you mentioned. So when is this expansion useful? So when is the theorem? I mean, in principle, this decomposition always applies to any time. But it becomes useful when you are in a situation like this. Yeah. At freeze out, you are just at the limiting. You're just, the limiting hypersurface where this applies. The gradients, you can calculate the gradients at the freeze out. Actually, this is very important to calculate, the polarization. You can calculate you can calculate the gradients at the freeze out. You can check this ratio and see how large it is and how it compares with presumably known mean free path. Of course, the mean free path, take into account the mean free path at the freeze out. So when you are near TC, is extremely small. Okay, this is what this ratio eta over S tells you, that the ratio between the mean free path. So that is some equal. The mean free path is extremely small. Okay. Yep. Well, yeah, in a sense, of course it is. If it is small, no, not necessarily. So, but yeah, it is. Well, not necessarily, I would say. So you may have a situation where you have, for instance, nabla mu beta nu plus nabla nu beta mu different from 0 and yet small. Okay. So in order to assess, for instance, what is the deviation from the Killing vector condition, you may write some ratio like this. I'm sorry for my loose reasoning. Okay, you may, for instance, compare the symmetric part to the antisymmetric part. Okay, make this ratio, and this tells you what is, a ratio. What is the deviation from the Killing vector? So how far I am from an equilibrium situation. But this tells you something different, okay? So you may have a situation. By the way, that is an important point to be stressed, that nabla mu beta nu in natural units, it's adimensional, by the way. So it's really adimensional because beta has the dimension of 1 over energy. So we have nabla mu is 1 over length, and therefore in natural units, this is adimensional. So we can really, in natural units, we can really gauge this with a number, a dimensional number, which is, can be larger than 1 or less than 1. So in relativistic heavy ion collisions, for instance, near the freeze out, both these numbers are much less than 1 in natural units, okay? However, their ratio is not close to 0. Okay, this is something which is of the order of 1 in an actual, say, collision at the final stage. Yeah. This is a requirement which is needed in order to treat this term as small compared to this. And what we do this is that we apply the linear response theory. As I said, assume you have a density operator which is an exponential of 2 terms, and the first one is supposedly large, and the second is supposedly the small correction. Z is the trace of of exponential of A plus B, and this, of course, in order to have the trace of rho equal 1. Okay. Now there is a well-established technique to make this to expand this exponential of operators in terms of B, which is an operator. Therefore, you cannot assume that they commute. So in the case of non-commuting case, in the case of commuting case, it is trivial. It is just the expansion of the exponential. If they are non-commuting, which is most likely the case, and in particular in this case, they are non-commuting, then you can take advantage of the so-called Kubo identity. which is an identity of this form involving the integral of over some real parameter z of this combination. So this is a very useful identity. Why? Because this, first of all, it tells you that it gives you some expansion at, it takes down, in other words, it takes down B, okay? Gives you the first term of an expansion in B, okay? And moreover, the important point, it can be iterated because you have, within the integral, you have the appearance of ZA plus B. And then, of course, you can use this identity in turn in order to get a quadratic approximation because you will take down once more B, which will be surrounded by two exponentials, and so on and so forth. So this is a sort of expansion like iterated expansion like the Dyson-Schwinger series. Okay. Now, if you stopping at the linear order means that we take an approximation of neglecting B within the integral here. And so retaining just the first order expansion in B. So we have an expression of this sort. Exponent of A plus B is equal approximately, so that E to the A, which is multiplied identity, and then plus this term. Notice that this integral matters because B and A do not commute in general, okay? So you should not expect that you can take this on the other side and make this, then cancel out this exponential. This is for the exponential. Now you have to also to do this, to apply this expansion to the partition function. And what is now left after you have plugged this within the trace is that eventually rho as a whole, so the density operator can be expanded this way. So rho A times 1 minus the mean value of B calculated with the operator, density operator A, plus this integral involving rho d A at the, so there is a, here there is a bracket that should not be there. Let me, okay. Okay, is it clear? Is it clear the meaning of rho A? Rho A means, maybe I should have. Okay, rho A. Okay. So rho A means exponent of A divided by trace in order to normalize it. Okay. Good. Now that we have that, we can. So we have our formula. Okay. So we have a linear response theory in general of A and B. We can identify what A and B are in here. So we have the A is given by the first term minus the integral over the hypersurface at some later time, for instance, the freeze out, for instance, but not necessarily. T mu beta nu minus z g nu, and beta is the second term. So sorry, B is the second term, which is a small one, and it is a correction. And then we have now a dominant term and a correction, and we can use the linear expansion theory. Sorry, the linear response theory, where rho, which is, let me see. Okay, so we have said that rho is equal to the local equilibrium at the time or at hypersurface sigma naught. And this is rho LE is the one, rho LE is the one calculated at this hypersurface final here, or here, sigma t. okay? So this is just the actual one, and so this is the state that we had at the beginning, and this is the one which is obtained by using a final hypersurface at some future time t, or or for instance, if you want to have a specific example that the freeze at hypersurface. Now, what we can do? Well, once we have this expansion, we can calculate the mean value of any operator within the linear response theory. Okay, for instance, the stress energy tensor, if you want to work in hydrodynamics. But you may calculate anything else. If you want to calculate some other thing, why not? Okay, let's calculate the stress energy tensor and see what happens. Well, if you take the definition, which is that, so let me write here that T, so when you see this T mu nu x, that means trace of rho, T mu nu in general, okay? So that the mean value of T mu nu calculated with this original operator is equal to the mean value calculated with rho LE, so at the local equilibrium at the final time, plus this integral, okay? Involving the expectation values calculated again with rho LE, so that the local equilibrium at the final time. This involves you can see that this involves the subtraction of two terms, which can be written in a compact way as the mean value, or the correlator in a sense, of T mu nu, this combination, and this is here, there is a subscript here, C, which stands for connected. It means that we have to subtract the mean value of the two operators, actually of the T mu nu x and of this combination in turn. So this is just a shorthand, okay? Not to write down every time these differences, okay? And now what is our task? Our task is to replace, of course, B with this expression. And what we get is something like this. We get the T mu nu local equilibrium plus this expression involving, on one hand, there is an integral of a real parameter Z, and an integral, four-dimensional integral of the region B, of the region, sorry, which is encompassed by the two hypersurfaces, of a so-called correlator involving twice the stress energy tensor, okay? Plus there will be another term involving the correlator between T mu nu and the currents, T mu nu x e to the zeta e a t rho sigma, which is a function of y now, because now it's this is a dummy integration variable, e to the minus zeta e connected, multiplied by what? By, okay, here I went back to the non-covariant, say, notation where this is a partial derivative, so using Cartesian coordinates, del sigma beta, del rho beta sigma y. This is, in a nutshell, this is, well, not in a nutshell, but this is really at the root, this first, say, equation you see, this is at the root of the so-called Kubo formulae of say, and of the stress energy tensor. What we can do next? It involves an integration which is over, so you can see that you need to know in order to, to find, to calculate the stress energy tensor, you need to know what is the gradient of the beta everywhere, so within the whole region. However, in the hydrodynamic limit, what happens is this correlator here, this correlator has a very, so it's different from zero only in a very narrow region, in a region which is determined by microscopic scales around X. If you are in this regime where there is a separation between the hydrodynamic length, or which is the scale over which the fields vary significantly, and the microscopic lengths, which govern what is the distance between x and y, over which this is significantly different from 0, then you can approximate this gradient as the gradient in x. So this is just some usual, say, correspond to some, when you have an integral which is made of two factors, like in the saddle point expansion. So you have something which varies slowly, something which is quickly varying around some point x. Then you can separate. You can say approximate this with only the first term. You can take it out. Oops, sorry, there is a mistake here. That it should be x. Pardon. That it should be x. And so what you have here is that an expression of what the correction to the stress energy tensor looks like at the linear order in the gradients, okay? And then you can imagine that this eventually will lead to a formula of what? Of thermal conductivity, of bulk viscosity, and shear viscosity as well. And indeed, the Kubo formulae are obtained, actually were obtained in the first place by using this technique, okay? Well, there is some more work to be done here. That is not really negligible, but eventually you will be led to a formula expressing in terms of quantum operators what the shear viscosity is. And this is what is known as Kubo formula. Okay, so this is an example of what we can do by using this separation. We can, in other words, write down the actual value T mu nu x, which is by definition can be obtained as approximately as the local equilibrium at the point x, which is now to be calculated, plus corrections at this linear order in the gradients, okay? And you can, of course, expand this farther and farther, okay? And you may have quadratic, and you have say cubic, and so on and so forth. All right. Now, what is now important to know is what is T mu nu local equilibrium. So this is the last point of my lecture. So how to calculate T mu nu? So all these corrections, in a sense, require the calculation of combination of operators at local equilibrium at the time t. So what we need to know now is a technique. So we need to, say, find a method to calculate mean values at local equilibrium at the present time. So how can we do this? Let's write down again the definition. This is just this local equilibrium at time t, T mu nu x, which means, let me emphasize that you calculate this at the same point. So in other words, I'm using this back again. You want to calculate this x at hypersurface where you believe that local equilibrium is still a good approximation. And this is trace of e to the minus d sigma mu T mu nu beta nu at the time t minus zj mu, and then have t mu nu x with the same time. Now, again, to calculate this, you can take advantage of the separation between scales that was at the origin of the root of the previous expansion. And what you can say is the following. Well, I have to calculate some mean value of an operator at the point x, which belongs to this hypersurface. So the obvious idea would be, maybe this is determined by the fields, by the scalar field, or the scalar and vector fields at the point x. So this would be the, so this is what you expect, in a sense, that why, if I have a stress energy tensor, I want to calculate mean value of an operator at point x, maybe this is determined by the value of these fields of beta and zeta at the same point x. So it means that this determined, in view of the physical meaning that I have discussed this morning of the temperature, the forward velocity, the chemical potential at the same point where I'm calculating the stress energy tensor. Indeed, this is the case, okay? You can, in other words, make another expansion and say, okay, let me confine just to, let me avoid, please, using this zeta for the present. So let's forget about it, okay? Just concentrate on this first part of the local equilibrium operator. Well, what you can do is the following. That is a hypersurface where these points belong to. Let's expand beta nu around x. So why not? This is, in a general, this is y. So there is an integration variable here, which is dummy. Let's expand this beta nu y around x in a Taylor series like this. Okay. Then what is left is the following, is that I have an approximation I can write down, this sigma t mu nu y, and then I have beta nu x, which can be taken out because it's no longer integrated. Plus, and then I have del lambda beta nu x times the integral, which depends on x, so it can be taken out. This sigma mu, and then I have t mu nu, and then I have y minus x lambda, okay? Plus, well, I could continue. Well, I could go on, and then I go to any orders in this Taylor expansion of beta. But let's first, so let us now remember what my previous argument was, that if I have a gradient which is, say, small, right, I can treat this term as perhaps as a correction, because it is proportional to a gradient. And since I have done this with this gradient here, maybe I can do the same here, and I can regard this term as a correction to the main term, which is written here, which involves just the forward temperature vector in the same point where I want to calculate T mu nu. Well, and what is this? What is this operator? Do you remember? Yeah, exactly. That is the forward momentum. This is the forward momentum. I can do something similar here by separating the gradient into a symmetric and antisymmetric part. Because this is a contraction of a gradient of a vector field with this integral. And I can do the same here. And what I find is a very interesting expression, which is 1/2 the lambda beta nu minus the nu beta lambda let me see, times J nu lambda, okay, where this is the angular momentum operator, plus 1/2 the nu beta lambda plus the lambda beta nu times Q nu lambda nu, or nu lambda. This Q is equal Q lambda nu is d sigma nu t oops mu no t mu lambda x nu plus exchange of lambda nu. Okay. Now, interesting, right? So we have something which I have the antisymmetric derivative of the vector field here that now I can call, why not? Well, being inspired by global equilibrium case, I can call this thermal vorticity. And it is indeed, because it gives you the thermal vorticity as defined in the global equilibrium case. And what is about this? Well, this is, the attention on this term is very recent. It dates back to 2 years ago. It includes the shear tensor that you have seen in the Mike Strickland's lectures. This is more general because it also includes gradients of temperature and acceleration terms. And this is called thermal shear. It's called thermal shear just because it includes also gradients of temperature. So we have, at the first order in the expansion, the derivative expansion, we have a term which is omega, a term which is xi, and then you can go on and find second order derivatives and so on and so forth. If we stop here, then our goal is to calculate T mu nu local equilibrium is now the trace of e to the minus beta dot p, beta x dot p. There should be an x also here because this is, sorry. That is, made a mistake here. That is y minus x, right? Nu plus lambda nu. This is the angular momentum centered in x, and this is a tensor centered in x. Okay. There is a deep difference between these two. And the difference is that while the integrand of Jx, as we have seen, is 0, and this is a conserved quantity, this is not. Okay, this implies that is a big difference, big conceptual difference between them, because this is a tensor operator and this is not. Although it is a tensor, you know, in the indices, but it's not a tensor operator, a proper tensor operator. But let's forget that. Let's put this aside. And so let me write down, this is plus 1/2 omega dot jx, omega x. So this is thermal vorticity in x, double contracted with jx plus 1/2 xi, double contracted with q, plus blah, blah, blah. Okay, and then we have T mu x. So this is a way to calculate the mean value of the stress energy tensor at local equilibrium. If we stop at 0 order term, so we just retain this form, then we are left with something very familiar. T mu nu local equilibrium, x is approximately, or more approximately, because this is just an approximation, so this is twice an approximation, of trace e to the minus beta x dot p T mu nu. Now, do you know what this will lead to? Does somebody know, except my students? You know, this form can be calculated exactly. This is a problem that Andrea will try to work out this afternoon. This gives you the ideal form of the stress energy tensor. This will result in something like rho plus p beta nu, I'm emphasizing beta, right? Beta squared minus p g mu nu, okay? Where in this form, you can identify that this is an energy density and this is a pressure, okay? Then, but this is the ideal form, but we can continue, okay? We can continue and then we can try to expand, okay? Also this term, and we can use linear response theory or quadratic response theory to go further and find corrections. And this is something that will perhaps be surprising to you. The fact that at local equilibrium, the stress energy tensor, in principle, at least in principle, well, it depends, so the actual value will depend on the particular, say, theory that we are dealing with. But the stress energy tensor may have some terms depending on the gradients, even at local thermodynamic equilibrium. Unlike it is stated in some textbooks, that every time you have a gradient, this is necessarily out of equilibrium. No, this is not true. That is, you may have gradients at local equilibrium, and this expansion proves it, even though they are difficult to calculate. And it is also true that you may have terms depending on that it's a global equilibrium, when they depends on omega, which is a constant, in fact, but whereas omega is the gradient of the beta temperature. So you may have, for instance, correction at global equilibrium, and this has been shown at depending quadratically on the thermal vorticity, even at global equilibrium. Okay. At local equilibrium, you may have terms correction depending on the gradients, both symmetric and antisymmetric, which are not dissipative. So they are really equilibrium terms. Now, in order to understand what is the difference between dissipative and non-dissipative, you will have to wait the next lecture, okay? And so I think now I think it's time to stop here. And so I will resume this tomorrow morning. Well, I will show what is the difference between, there is a very important conceptual difference about what comes from this term and corrections, so the local equilibrium, and what comes from corrections due to this term, okay? And it can be proved that what comes from this term is non-dissipative, so it does not create entropy, and what comes from this term does create entropy. And so to summarize, what is in this expansion here, local equilibrium, will be corrections to the stress energy tensor of quantum origin, which will not create entropy. So they are non-dissipative, okay? It cannot enter in any way to contribute to the entropy generation, okay? Okay, so I think that I have no more time, so I should have, well, I would have, I would have, of course, as usual, I would have liked to tell you more, but time is up, so let me postpone this to tomorrow morning. Are there final questions before we go to lunch? Everybody start. Oh, there's one question. Yes, please. I have to speak louder because. Yes.
My question is, would be like, where does the provision of the choice of matching here? Because from what I see, there's an arbitrarity in the choice of the hypothesis.
Yeah. Yeah, exactly. Yes, that's a very good question, and this is something leading to the discussion of what is a frame in this formalism. Okay, in this quantum formalism, what is a frame? What is a matching condition? Well, I can say that a matching condition in general. So if you want to find, say, some correspondence with the classical, say, formulation. Instead, this is the matching condition. Okay, so this is the constraint that we have enforced at the very beginning. At the very beginning, we have enforced a constraint, which is that the mean value of the, which is the, I should know the energy density and momentum in order to calculate the local equilibrium. And we have used this condition. So what was that? This was the supposedly known stress energy tensor. Of course, there is no supposedly known stress energy in practice. And this is, what does this mean? That is the stress energy tensor, including T mu nu local equilibrium, and this plus, say, delta T mu nu local equilibrium. So plus the correction, sorry, plus delta T mu nu, okay, as obtained from an expansion. So if I was able, in other words, let me show you this calculation, okay? So if I was able to carry on this expansion, if I was able to carry this expansion to the infinite order, then I eventually will be able to calculate the mean value of T mu nu, right? Which is what I'm interested in. Okay, and this mean value of T mu nu is given by the local equilibrium plus something depending on the gradients at any order, okay? And now the matching condition is the following, is that if I project onto n mu, these are equal, and therefore this is 0. Okay? So this is a constraint that should not be forgotten. Of course, what is a good point of your statement is that this depends on which hypersurface that I have calculated. But eventually, this term cannot depend on it. So in other words, this hypersurface is a sort of, let me use this analogy, although it's not really fully appropriate. It's a sort of renormalization scheme. So I need to choose a hypersurface in order to calculate this T mu nu, able to that this value, the T mu nu, should not depend on it. I don't know if this was the question or if I answered your question at all. Maybe, but I think what? Yeah, sure, yes. T mu nu eventually should not depend on it, and it does not, in fact, because, yeah. Can I tell you something? That is, so if you T mu nu should not depend on the hypersurface because it does not depend on X, so cannot depend on the hypersurface that you have chosen. Maybe I can stress this point tomorrow morning. However, that any truncated calculation depends on the hypersurface. That's final conclusion. Maybe this is a conclusion that you can agree with. So only if you were able to extend this calculation to infinite order, then this dependence on sigma will be lost. But I can stress this point tomorrow morning for everybody. Yeah, I think this is a very important point. So, okay, I think that we can